Okay, anybody else? Thank you for that. Okay, any other questions before I move on? Okay, so you got an, excuse me, you got an email from me to print out the table. So I hope you guys got that email, right? So I hope you have the table with you. We're going to be using this table for the next 2 chapters. So it's going to be really important to have that. And this is kind of, after that second midterm, this is when we start to bring everything together. So it's not as many new concepts as it is starting to integrate and apply the concepts that we've already learned. So we have chapter 8 now, and then we're doing chapter 11 and then chapter 10. And those are our last 3 chapters. So chapter 8 is on responses to exercise, and chapter 11, our next chapter, is on adaptations to training. So I'm going to be using the terms exercise and training to mean different things. So if you think about how we normally use the terms exercise and training, and I usually ask people what they think the difference is, and normally what people say is exercise is more general for like health and fitness, and training is more specific for like an athlete training for a specific event. And it's fair to use the words that way, and they probably are commonly used that way, but that's not how we're going to be using the terms. So let me explain to you how we're going to be using the terms so that we're clear and we're on the same page. Okay? When I use the term exercise, I'm referring to acute exercise, one bout of exercise of increasing intensity. So if you're, for example, running and you increase your intensity from 4 miles per hour to 5 miles per hour to 6 miles per hour and 7 miles per hour, how is your body going to respond to that? That's responses to exercise. That's chapter 8. Chapter 11 is adaptations to training. When I use the word training, it refers to chronic training, chronic aerobic endurance training. So if you were to run 5 times a week for a period of a year, what changes are going to occur in your body as an adaptation to that chronic stimulus? Okay, that's different from how's your body going to respond to an increase in speed right now in this moment, acute, and that's exercise, versus if you give the body a chronic stimulus, what adaptations will you see? And then how will that affect your exercise? Okay, do you kind of understand the difference? So you have this table, and if you look at the table, going down the left side of the table, you have all the different variables we've discussed. Heart rate, stroke volume, cardiac output, AVO2 difference, lactate threshold, VO2 max, all the different terminology we've been using and the concepts we've been talking about. So that's listed down on the left side, and then the first column is what happens to that with increased intensity. So we're going to talk about what happens to each of those variables as you increase your exercise intensity. It's either going to, that first column is either going to be increase, decrease, or stay the same, and I just have arrows, up, down, or stay the same. Okay, the next column says why. So we're going to have a physiological explanation for why those things are occurring in response to exercise. Okay, we're going to fill out those first 2 columns on both sides of the table. That's going to be chapter 8. Okay, chapter 11 is going to go to the next table that says, the next column on the table that says what happens with training. So what happens to these same variables if you apply a chronic training stimulus, and this is specifically endurance training. Okay, when we get to chapter 10, that's going to be anaerobic training, which is going to be high intensity interval training and resistance training. Right now on this table, we're talking about aerobic endurance training. Okay, Caroline, you have a question?
Yeah, so for our notes, are we mainly just using like this table, would you say?
So yes and no. You're going to want to fill in this table as we go along, but you're also going to want separate paper because I'm definitely giving you more information than can fit on that table.
Okay.
You're going to want both.
Okay.
Yeah. So it's going to take us several lectures to fill out this table because it's 2 chapters long. And by the time we finish that, there's going to be a lot of very important information on here that you're going to need for your final and that you're also going to need for 446. Okay, so this is going to be a very helpful tool for you to organize all this information. Okay? questions on any of that, how this is going to work? Okay, so I'm going to start. Okay. There's only 25 people here. That's not good. These next few lectures are not only super important, but they're going to be the super interesting ones as we start integrating and applying the information. So I hope that people come to these last couple weeks of lectures. So we're going to start on page 1 with the first variable, and that is resting heart rate. Okay. Olivia, what's a normal resting heart rate?
Normal resting heart rate is between 60 to 80 beats per minute. 70 to 80 beats per minute.
Nicole, what's a normal resting heart rate?
Normal resting heart rate, isn't it 100 beats per minute?
Cindy, what's the normal resting heart rate?
It would depend on your like different variables of a person, like if they're trained or untrained and weight and whatnot.
Chris, what's a normal resting heart rate?
80 to 100.
Sydney, what's a normal resting heart rate?
60 to 80 in a trained population and 80 to 100 in untrained.
Okay, so 60 to 100 is considered normal, right? Anything under 60 was abnormally low, that we called bradycardia. Anything over 100 was abnormally high, that was called tachycardia. Anything between 60 and 100 is considered normal. And we did say that trained people tend to be on the lower end and untrained people tend to be on the higher end of that range. And we'll talk about why that is when we get to the training chapter, because training definitely does affect that, okay? But normal resting heart rate, anywhere between 60 and 100 beats per minute. Okay, so the question is, what happens to your resting heart rate as your exercise intensity increases? Does it increase, decrease, or stay the same?
It increases.
Increases.
Why?
Increase in SNS activity.
Okay, does everybody agree with that?
Yes.
Does anybody not agree with that?
Wouldn't it first be a parasympathetic decrease?
Okay. Let me ask you the question again. What happens to your resting heart rate as your exercise intensity increases? Does it increase, decrease, or stay the same?
Increases.
Ismail, what do you think?
I think it increases because
Because?
of the 3 things that we mentioned. It was the release of epinephrine, it acts on the sympathetic cardiac nerve, and the vagus nerves also.
Okay, everybody agrees with that?
Wait, are you, but it is just resting heart rate, right? So
That's
I'm,
the resting heart rate.
I know your heart rate goes up, but like
When you're at rest, it doesn't.
when you're, yeah, like the resting, wouldn't that just stay the same?
Because resting is a different type of heart rate, and if you're, wow, what's like normal when you're doing something, obviously it's gonna spike up. But at this point, you're staying the same.
But she said when you start to work out, when you start to exercise.
Yeah.
As exercise intensity increases. So if you're already exercising and the intensity increases, shouldn't it increase? Wouldn't that be the sympathetic nervous system?
I feel like maybe I'm thinking about it too much.
Yeah.
Yeah.
I think
I want you guys to discuss this and come up with an answer.
I mean,
I think unless
resting heart rate, like the base of it will get lower because you train more, and so that gets lower as a general. But as you work out, it increases. But your base resting heart rate decreases the more trained you become.
But that
that's
would
what I
be
was gonna say. I was gonna say that.
not with just like base exercise intensity, because that's like acute exercise versus the chronic exercise training.
And Nick, what do you want to say?
Well, based on the definitions that you gave earlier, when we talk about exercise, you said that was one bout of like physical activity compared to training, and training is a chronic stimulus. So I don't think one exercise session is enough to actually reduce your resting heart rate. I think it would just increase your normal heart rate during exercise, but I don't think, going on a 2-mile run would be enough to change your resting heart rate.
So did somebody say resting heart rate is decreasing? Because I only heard increase.
I said decreasing. If the more you train, it will decrease.
Okay, so listen to the question. Remember, we're not talking about training right now, we're talking about exercise. Increasing exercise intensity, so going from 4 miles per hour to 5 miles per hour and 6 miles per hour. That's our exercise. Increase exercise intensity. What happens to your resting heart rate as your exercise intensity increases? Does it increase, decrease, or stay the same?
Decrease.
I think it stays the same.
I agree. I think it stays the same too.
I think it stays the same.
During exercise?
As your exercise intensity increases, what happens to your resting heart rate? Jasmine, what do you think?
Increases.
Increase.
I want to say that I agree with Cindy that it does decrease, but I don't know. I'm still not sure.
Sydney, what do you think?
I think it stays the same just because somebody said it was like a baseline, and as you're exercising, that would become a submax heart rate, I think, and that would increase with exercise, but with your resting heart rate would stay the same no matter what it is.
So this is where we're going to get into some critical thinking. Okay, you have to understand these terms and to be able to assess the situation and apply your knowledge using the terms appropriately. Okay, think about what is a resting heart rate. Your resting heart rate is your heart rate when you're resting. It's the lowest your heart rate can go when you're most relaxed, which normally is between 60 and 100. If you start increasing your exercise intensity, your heart rate's going to go up. Maybe your heart rate goes up to 120, 140 while you're running. Is that your resting heart rate?
No.
That's your submax heart rate. Remember, we have a resting heart rate, which is the lowest your heart rate can go. We have a max heart rate, which is the highest your heart rate can go, which is 220 minus your age, right? Anything in between is submax. So if you're let's say your resting heart rate is 70, you start running, your heart rate increases to 130. Your resting heart rate is still 70, you're just not at it anymore. Does that make sense? Now you're at your submax heart rate. Okay, so what happens to resting heart rate as exercise intensity increases? Increase, decrease, or stay the same?
Same.
It stays the same. Your resting heart rate is not affected by exercise intensity. It will be affected by training. As we already said, a trained person will have a lower resting heart rate. We'll talk about why that is in the next chapter. Right now we're talking about what happens to it as you increase your exercise intensity. Your resting heart rate is not affected by your exercise intensity. Okay, so what I have on my table is I just put stays the same, not affected. Okay, let's go to max heart rate. What happens to max heart rate as your exercise intensity increases? Does it increase, decrease, or stay the same?
Increase.
I heard stay the same and increase.
I think it stays the same also.
Okay, why does it
Stays the
stay the same?
same.
What does your max heart rate depend on?
Your age.
220
minus your age. Your fitness, your exercise intensity, not involved in there. This one's not even affected by fitness. It's your age, 220 minus your age. Okay, your resting heart rate and your max heart rate are not going to change if you increase the speed on the treadmill. What's going to change is your submax. Okay, so the next one is submax heart rate. What happens to your submax heart rate as your exercise intensity increases?
It increases.
That increases.
It increases.
Mhm.
Why?
Mhm.
Why? Or how?
For the reasons we mentioned earlier, with the increased sympathetic nervous system activity.
Specifically,
Epinephrine,
epinephrine,
sympathetic cardiac nerve.
sympathetic cardiac nerve, and like Tito said, the decrease in the parasympathetic nervous system activity, the decrease in vagal tone.
Vagal tone.
Okay, we have a graph for that, right? As exercise intensity increases, heart rate increases, and we have the explanations for why. What's acting on the SA node to cause the increases from 60 all the way up to 200. We have explanation for what's causing those increases. Okay, any questions on that? So that's what goes in your Y box. So max heart rate is increasing. In your Y box, you need to explain why. Okay, that's not new information. We already learned that. We okay? Okay, next one is AVO2 difference max. So before we go into that one, let's define it. Harrison, what is AVO2 difference?
Just the different oxygen levels in between your blood and your atrial blood.
Between the arterial blood
Arterial.
and the venous blood,
Mm-hmm.
right? The difference in the oxygen content between the arterial blood and the venous blood. And what does that reflect?
Oxygen consumption in the muscle.
Oxygen consumption in the muscle. Because the more oxygen the muscle consumes, the bigger the difference will be in the venous, in the oxygen content. Okay, so on the table we have AVO2 difference max and AVO2 difference submax. There's also rest, but we're not going to talk about rest. We're going to talk about max and submax. So AVO2 difference max would basically be the muscle's maximum capacity to consume oxygen, which would give you the maximum difference between oxygen content in the artery and the veins. So what happens to AVO2 difference max as exercise intensity increases? Does it increase, decrease, or stay the same?
Stay the same.
Stays the same. It's a max level. There isn't really any max capacity that's going to be affected by you increasing your exercise intensity. If you speed up your treadmill from 5 miles per hour to 6 miles per hour, that's not going to affect your AVO2 difference max. Okay, AVO2 difference submax. What happens to AVO2 difference submax as your exercise intensity increases?
It'll increase.
It should increase.
Why?
Because the muscles need to consume more oxygen during exercise.
Exactly. As you increase your exercise intensity, the muscles consume more oxygen. That's going to cause a bigger difference between the oxygen content in the artery and the veins, which is AVO2 difference. So as intensity goes up, AVO2 difference submax goes up. Muscle consumes more oxygen. Okay, then we have stroke volume max and stroke volume submax. London, what is the definition of stroke volume?
In systolic volume minus in systolic volume.
Okay, that's the formula. What's the definition in word?
It's the amount of blood pumped per beat.
Amount of blood pumped by the left ventricle per beat. Good. So stroke volume max would be the maximum amount of blood the left ventricle could pump in 1 beat. What happens to max stroke volume as exercise intensity increases?
Nothing.
Stays the same. It's a max value. Your maximum capacity is not going to be affected by your exercise intensity. How about submax?
Increases?
It should increase.
Max stroke volume will increase as your exercise intensity increases. Okay, to talk about why, I'm going to put my whiteboard up and clear this. Okay, so to talk about what's affecting stroke volume, we need to write the formula for stroke volume, which London already told us. Stroke volume equals, I'm going to spread this out because we're going to be adding a lot of information here. end diastolic volume minus end systolic volume. Okay, so we already said we know stroke volume is going to be increasing. The amount of blood that comes out with each contraction of the ventricle is going to increase as our intensity increases. James, what is the definition of end diastolic volume?
It's the amount of blood left in the ventricles after diastole.
After diastole. What is the ventricle doing during diastole?
They should be filling and relaxing.
Yeah, it's relaxed and filling. So we want end diastolic volume to be high. An increase in end diastolic volume means we're getting more blood into the ventricle, which is going to help us get blood out of the ventricle. Okay. Anthony, what is end systolic volume? Olivia, what is end systolic volume?
The amount of blood left in the left ventricle after systole.
After systole, and what is the ventricle doing during systole?
The ventricle is contracting.
Contracting and emptying. So we want the amount of blood that's in the ventricle after we empty it to be low in order to get the most blood out of it possible. Okay, so in order to get an increase in stroke volume, we need an increase in end diastolic volume and a decrease in end systolic volume. Okay, end diastolic volume depends on two things. End systolic volume depends on two things. The amount of blood you get into the ventricle, which is end diastolic volume, depends on how much blood you bring back to the heart. That's venous return. The more blood we can bring back to the heart from the body, the more blood we can get into the ventricle. Makes sense. We talked about a few things that increase venous return. What are they?
Vasoconstriction.
Skeletal muscle pump.
Respiratory pump, and vasoconstriction. These are venous return mechanisms, right? So okay, so these are three venous return mechanisms that are causing an increase in venous return. What's activating the skeletal muscle pump?
Contraction of the muscle.
Muscle contraction. MM is an abbreviation for muscle, which is happening because we're exercising. Okay, so we start exercising, we're contracting our muscles, that activates the skeletal muscle pump, which increases venous return. That venous return will increase end diastolic volume, which will increase stroke volume. Okay, what's activating the respiratory pump?
The inhalations.
Increased ventilation rate, breathing faster, right? It's the inspiration and expiration, that pulmonary ventilation, that activates the respiratory pump. What are still some things that cause an increased ventilation rate during exercise? There are two that we talked about.
Inspiration and expiration.
Well, that is the pulmonary ventilation. What causes the increase in pulmonary ventilation rate during exercise?
High CO2 and low O2.
Carbon dioxide triggers the inspiratory centers in your brain to increase your ventilation rate. Do you remember what the other one was?
O2, low O2.
CO2.
Is it the gas gradient?
Gas gradient causes the air to move. It doesn't increase your rate of ventilation. The other thing that increases your rate of ventilation, remember I said, if I ask you what causes something and you don't know, this is a good guess.
Epinephrine.
Epinephrine. So epinephrine and carbon dioxide are the two things that act on the inspiratory centers in your brain to cause you to breathe faster. Okay, I'm going to just put epinephrine on here to simplify your life, but you could put the carbon dioxide on here as well, but you'd have to track what's causing the increase in carbon dioxide. I'm just going to put epinephrine. What's causing the release of epinephrine?
The sympathetic nervous system.
Increased sympathetic nervous system activity as triggered by exercise. Okay, so you start exercising, increases activity of the sympathetic nervous system, which causes a release of epinephrine. That causes an increase in your ventilation rate, you're breathing faster, which activates the respiratory pump. This increases venous return, which increases end diastolic volume, which increases stroke volume. Okay, remember the whole question we're answering here right now is how does exercise intensity cause an increase in stroke volume? That's what we're explaining in detail. Okay, what's causing vasoconstriction?
Arterioles.
Arterioles are vasoconstricting. Okay, what's causing the arterioles to vasoconstrict?
Epinephrine.
Okay. So can I just do this? Epinephrine is acting on the arterioles, causing vasoconstriction, which increases venous return, increases end diastolic volume, increases stroke volume. Everybody okay with that? So I don't have to draw a whole separate branch here that's exactly the same as this one. Yes?
Yes.
Okay. This second branch of end diastolic volume, I'm going to skip for a moment. I'm going to come back to it. I'm going to go over to end systolic volume next. What did we say is the effector for stroke volume?
SA node?
No, that's heart rate.
Sorry.
Left ventricular myocardium.
Left ventricular myocardium. If we can get that muscle to contract more forcefully, we get more blood out, which is an increase in stroke volume, which means we have less blood left in, which is a decrease in end systolic volume. Okay, so that means left ventricular contractility is the ability of that left ventricle to contract forcefully. So this is going to be an increase in contractility, which is happening at the left ventricular myocardium. What is acting on that to cause the increased contraction strength?
Vasoconstriction.
What acts on the left ventricular myocardium to cause it to increase its contraction strength? Epinephrine. That was part of our blood pressure map. Okay, that's released as part of increased sympathetic nervous system activity in response to exercise. So you exercise, increase sympathetic nervous system activity, release epinephrine, acts on the left ventricular myocardium to increase contractility, which just means it's going to contract more forcefully. That increased contraction strength is going to increase stroke volume, which is going to decrease end systolic volume. Okay, the other thing that's going to affect your end systolic volume is resistance. So we talked about peripheral resistance. This is more resistance at the aorta that the heart is directly working against. So if resistance is high, there's resistance to the blood coming out of the ventricle. That means it's going to be hard to get blood out. If resistance is high, it's hard to get blood out. That will decrease your stroke volume and make more blood be left in. If it's harder to get the blood out, more is going to be left in. That would be an increase in end systolic volume. So what we need is a decrease in resistance, so it's easier to get blood out, So we'll have an increase in stroke volume and therefore a decrease in end systolic volume and have less blood left in the heart. Okay, so this resistance is not exactly the same as peripheral resistance, is more distal at the resistance to blood flow at the muscle, whereas this is resistance to blood flow coming out of the ventricle. I'll kind of use the terms interchangeably, but just know that they're slightly different. You could put peripheral resistance here. I wouldn't mark it wrong, but it's really resistance. So what will cause a decrease in resistance?
Decreasing radius?
Decreasing radius?
Or, oh no, I increased, I'm sorry.
Increased vessel radius, which would be caused by vasodilation. Okay, this is happening at the arterioles, right? The arterioles need to vasodilate in order to increase vessel radius and decrease resistance. What is going to cause the arterioles to vasodilate?
Epinephrine.
Epinephrine.
Does epinephrine cause vasodilation? It's, what's that called?
Patholysis.
When the local conditions at the exercising muscle cause vasodilation.
Arterial autoregulation.
It's triggered by the local conditions at the exercising muscle, which you should be able to list at this point. Okay, I'm not going to go over them again. I expect you to know those. Okay, that's triggered by muscle contraction due to exercise. Okay, so stay with me here. You start exercising, you're contracting your muscles. That creates these local conditions at the exercising muscle, which triggers arterial autoregulation. That causes the arterioles to vasodilate, which increases the vessel radius and decreases resistance. That decrease in resistance is going to allow you to get more blood out of the ventricle, which is an increase in stroke volume, and leave less blood in the ventricle, which is a decrease in end systolic volume. Questions?
I have a quick question. During like the part where we list local conditions, do we have to mention like the chemoreceptor?
You don't. You could put chemoreceptors, could be a separate thing here if you wanted to put that. I'm trying to simplify it a little bit and not put all of the details, but yes, that could absolutely be in there.
Thank you.
Okay, so I have one more thing to add here under end diastolic volume, and that is increased left ventricular distensibility. Distensibility means the ability to stretch or distend. Okay, so if you think about, if you're going to fill up a water balloon, if you take an empty, you know, the water balloons are small, right? If you take an empty balloon, it's small, but if we fill it with water, it stretches to accommodate the water, right? So distensibility is the ability of the balloon to stretch. The more it can stretch, the more blood we can fit into it. Okay, so the question is, with that water balloon, if when you take the empty water balloon and you put it over the faucet and then you turn the water on, is the balloon stretching in anticipation of the water coming in, or is the water coming in causing the balloon to stretch?
The water is causing the
water coming in.
Right. So same thing with the ventricle. The ventricle is not going to stretch out in anticipation of filling with blood, but because we have, sorry, I'm changing my color. Because we have such a massive increase in venous return, that's like turning on the water faucet. That's going to then cause the ventricle to stretch and increase left ventricular distensibility. So all the blood returning to the heart is going to cause the ventricle to stretch. That's important. Think about our skeletal muscles. When we stretch our skeletal muscles, how do they respond?
They go back. They try to.
They contract.
They contract. Yeah.
What's that called?
Stretch reflex?
Stretch reflex. You stretch a muscle, it responds immediately with a forceful contraction. Stretch reflex. Same thing happens in the cardiac muscle. When you stretch it, it responds with a more forceful contraction. But in the cardiac muscle, we don't call it the stretch reflex. In the cardiac muscle, we call it the Frank-Starling mechanism. Frank-Starling mechanism is when you stretch the left ventricle, it responds with a more forceful contraction. Okay, so we have all these venous return mechanisms occurring during exercise that are going to bring this massive blood flow into the heart, which is going to cause it to stretch. That distensibility is going to trigger the Frank-Starling mechanism, which is in turn going to increase left ventricular contractility. Okay, so we have two things here causing an increase in left ventricular contractility. One of them is the epinephrine acting on the left ventricular myocardium. One of them is the stretching of the ventricle triggering the Frank-Starling mechanism. They're both going to cause the ventricle to contract more forcefully, which is going to cause you to get more blood out, which is an increase in stroke volume, which means less blood is left in, which is a decrease in end systolic volume. Okay, so this entire flow chart answers the question, how does exercise cause an increase in stroke volume? Okay, there's a lot of overlap here, just like when we drew the blood pressure map. And we can simplify this into a concept map with exercise at the top, increased stroke volume at the bottom. From exercise, how many different unique branches do we have?
Four.
5.
4 or 5? What are they?
Isn't it 2?
Yeah, isn't it 2?
What are they?
Muscle contraction
Muscle
and
contraction is 1.
increase in sympathetic nervous system activity.
And increased sympathetic nervous system activity is the other. Okay, muscle contraction is going to activate the skeletal muscle pump and cause arterial autoregulation. Sympathetic nervous system is going to cause a release of epinephrine, which is going to cause a few different things. Okay, so we're going to do just like we did with the blood pressure map. We're going to flip this over and simplify it to organize the information. Okay, so you should have this written down on your paper, put it off to the side. If you want to screenshot this, you can, because I'm about to erase it.
Can you repeat again? There was 2, muscle contraction and what, and increase the
sympathetic nervous system activity.
Could you go over the Frank-Starling mechanism one more time?
Yes, Frank-Starling mechanism is like the stretch reflex in the cardiac muscle. When you stretch the ventricle, it responds with a more forceful contraction. Okay, I'm going to clear this page. Take a screenshot real quick if you want it. Okay, same information, a little more organized. I'm going to start with exercise at the top. Don't want it to be green though. Let's do. So this is answering the question, what causes the increase in submax stroke volume during exercise? So how many different branches do we have here?
2.
What are they?
Increased SNS activity, sympathetic nervous system, and muscle contraction.
Let's to the muscle contraction side first. How many different branches do we have from muscle contraction?
Two.
What are they?
Skeletal muscle pump and local conditions.
Local conditions and skeletal muscle pump. So thinking about which one I'm going to put where is going to make a difference, because remember, when I'm building this map, I can't cross lines. So I know that I'm going to have 3 different things affecting venous return, right? We have our 3 different venous return mechanisms. One of them is going to come from muscle contraction, and the other is going to come from sympathetic side. So I know that those are going to need to meet. So that means I need to put the muscle pump on the inside here. If I put it on the outside, I'm going to end up crossing over. Okay, so I'm going to do this one on the inside. Okay, so muscle contraction activates the skeletal muscle pump, which causes what?
Venous return increase.
Okay, which causes what?
Increase in end diastolic volume.
Which causes what?
Increase in stroke volume.
Okay, which is what we're trying to get to. Okay, all pathways are going to end at that increase in stroke volume. That increase in end diastolic volume also causes something else. What is it?
The increased left ventricular distensibility.
Which causes what?
FSM.
Triggers. What does FSM stand for?
Frank-Starling mechanism.
Triggers the Frank-Starling mechanism, which causes what?
Increase in left ventricular contractility.
Which will cause an increase in stroke volume. Okay, so that increase in end diastolic volume independently will cause an increase in stroke volume. Get more blood to the heart, you'll get more blood out of the heart. But in addition to that, it also stretches the ventricle, which triggers the Frank-Starling mechanism, which causes it to contract more forcefully, which means you get more blood out of it. Notice that I don't have a decrease in end systolic volume here, because technically the decrease in end systolic volume doesn't happen until after the increase in stroke volume. We don't know how much blood is going to be left in the ventricle till after we empty it. So the decrease in end systolic volume technically should go after the increase in stroke volume, and we're not concerned about that. We're just concerned about stroke volume, so I'm not putting it on there. If you were to put the decreased end systolic volume here in between contractility and stroke volume, I wouldn't mark that off, because I understand the logic of following that formula, and this leads to the decreased end systolic volume. So if you put it there, I won't mark it wrong, but technically it comes after the increase in stroke volume. We okay so far?
Yes.
Okay, what's the other branch of muscle contraction?
Six local conditions.
Okay, so muscle contraction creates local conditions, which you should be able to list. So in any explanation of this should include that list. That's going to trigger, oops, I want that to be red. Going to trigger what?
Arterial autoregulation.
And you could include the chemoreceptors in there if you want to as a step before this. Arterial autoregulation is going to cause what?
Vasodilation.
Which is going to cause what?
Increased vessel radius.
Which will cause what?
Decrease in resistance.
Arterial autoregulation causes vasodilation, which increases the vessel radius, which decreases resistance, which increases stroke volume. So again, you could put decreased end systolic volume here. I would be okay with that. You could put decreased peripheral resistance here. I wouldn't mark that wrong. Okay, but I'm just going to say resistance, so it's slightly different. Okay, we okay with that side of the map?
Yes.
Stop me if you're not. Okay, on the increased sympathetic nervous system activity side, how many branches do we have?
3.
Okay, what are
There's
they?
just one for epinephrine.
Okay, does everybody agree with that? Are there 1 or are there 3?
1, 2.
Oh,
If there's 2, what are they?
Is it epinephrine and arterials?
Isn't the epinephrine acting on the arterioles?
Oh, yeah.
Okay, so how many branches do we have coming off of epinephrine?
2.
3.
I heard a 2 and I heard a 3.
3.
Okay, what are they?
Increased
Ventilation rate.
ventilation rate.
Vasoconstriction.
Acting on the arterioles to cause vasoconstriction.
And left ventricular myocardium.
Acting on the myocardium to cause contraction strength. And what's the third?
Increase of ventilation rate.
Increasing the ventilation rate. Okay, which is going to lead to venous return. Okay, so we have to think about which ones we're going to put where, and we can't cross lines. So 2 of these are going to end up connecting to increased venous return, and the third is not. So we just have to make sure that the one that's not going to connect to increased venous return goes on the outside. Okay, what's that one going to be? The one that's not going to connect to venous return?
Left ventricular myocardium.
So let's save that one for later. Let's do the other ones here. So with these 2, it doesn't matter which one goes first. So what should we put here?
About the arterioles.
Okay, how do the arterioles respond to epinephrine?
Vasoconstriction.
Okay, which will cause
Increased venous return.
increased venous return. Okay, so you start exercising, it increases your sympathetic nervous system activity, which causes the release of epinephrine. That acts on the arterioles, which causes vasoconstriction, which increases venous return. And from there, everything else is the same. Okay, what else does the epinephrine act on here? What else does it cause?
Increased ventilation.
Ventilation.
Which triggers
The respiratory pump.
causes what?
Increases venous return.
Okay. How does the left ventricular myocardium respond to epinephrine?
An increase in contraction strength.
Increase in contractility. So if we want to, we can connect that right here. Okay, so this is a map that details the explanation for what's causing the increases in stroke volume, submax stroke volume during exercise. So that's what goes in the Y box on your table. Okay, increased submax stroke volume during exercise because, so you can put on there C table, C map, and you know that this map goes in there. You obviously can't fit it in that box. But I'm also going to give you a shortened version of this answer that you can put in the box. But I'm going to wait for a second for that because I want to talk about this first. So if we were taking tests in class, I would probably ask you to draw this. I'm not going to be having you draw it on this online test, but I will be asking you questions about it. So being able to draw it will help you answer questions, just like being able to draw the blood pressure map will. But something I want to point out to you on here, and that is that here we have vasoconstriction, and here we have vasodilation. How is it possible, or is it possible, that both of those things are happening during exercise?
So sympatholysis.
Okay, so sympatholysis would say that we're getting vasodilation instead of vasoconstriction. So are we also getting vasoconstriction? Is that possible? Or is it one or the other?
Is it because it's at different areas of the body?
Exactly. During exercise, we're having vasodilation at the exercising muscle due to sympatholysis and at the vessels near the skin for thermoregulation. Everywhere else is having vasoconstriction. Okay, so we are having vasodilation and vasoconstriction both occurring during exercise at different locations, and both of those things are contributing to increases in stroke volume in different ways. Okay, the vasodilation is increasing vessel radius and decreasing resistance. The vasoconstriction is increasing venous return and increasing end diastolic volume. Okay, so they're both occurring at the same time in different locations. They're both contributing to an increase in stroke volume. And I think that's a really good exam question. During exercise, are you getting vasodilation or vasoconstriction or both? How are they contributing, or which one is contributing to stroke volume, or how are they contributing to stroke volume? Something about how we're able to have both at the same time and how they both contribute to stroke volume. Okay, or anything else on this map that you need to be prepared to explain.
Can you repeat where it happened again, muscle and the skin?
Well, vasodilation is occurring at the exercising muscle, right? This is sympatholysis. When we get vasodilation at the exercising muscle, that's sympatholysis. And we also get vasodilation, the vessels near the skin. That's not on this map. We could put it on here. That's a result of epinephrine. Okay, so we could put a whole separate branch on here. Epinephrine acts on the vessels near the skin, causes them to vasodilate, which it decreases resistance. We could put that on here too, okay, but I'm trying to simplify your life. They're getting vasodilation in those two places. Pretty much everywhere else is vasoconstricting. Okay, questions on this map, anything on it, or how to use it to answer questions?
Can you explain the purple part again, like, and why it's like you put it in a different color?
I put a different color just so you could see it as a different pathway, just to help you visualize it, because this increase in end diastolic volume, even without the desensibility, the increase in end diastolic volume means we're having more blood come to the heart, right? We have an increased venous return, more blood coming to the heart, which means more blood coming out of the heart independently. But this end diastolic volume is also causing the ventricle to stretch. And that's going to trigger the Frank-Starling mechanism and give us contractility. So I could say explain 2 different ways that an increase in end diastolic volume contributes to increases in stroke volume. And that would be, first of all, just because the fact that you have more blood in there means you can get more blood out. And second, because it's triggering the Frank-Starling mechanism.
Okay, got it. Thank you.
Okay, anything else on this? Okay, screenshot this if you want to, if you haven't yet, because I'm about to erase it. And I'm going to give you a shortened version of the answer that you can actually write into your table. So to simplify this, I'm going to write the formula again. Stroke volume equals end diastolic volume minus end systolic volume. End diastolic volume depended on 2 things, and systolic volume depended on 2 things. What are they?
Increased venous
Increasing
return,
venous return.
and increased left ventricular distensibility.
What goes under end systolic volume?
Left ventricular contractility and decreased resistance.
Okay, so an increase in stroke volume during exercise, submax, is due to an increase in end diastolic volume. That's caused by an increase in venous return and an increase in ventricular distensibility. We also have a decrease in end systolic volume, which is caused by an increase in left ventricular contractility and a decrease in resistance. Okay, this is a short version of explaining what's causing the increases in stroke volume. But of course, we have a lot of details we can add here that bring the map in. Okay, so you have a short version of this answer. This you can fit in the box, in the Y box on your table, and then make sure you connect this with the big concept map we just drew. Okay, questions on that? Okay, we're just going to do cardiac output real quick and then we'll stop. So the next one on the table is max cardiac output. Svetlana, what is the definition of cardiac output?
Is it the amount of blood pumped by the left ventricle per beat?
Per beat of stroke volume.
I mean, per minute.
Per minute is cardiac output. Okay, so max cardiac output would be the maximum amount of blood the left ventricle could pump in 1 minute. What do you think happens to max cardiac output as exercise intensity increases?
Stays the same.
Stays the same. It's a max value. Max values are not affected by exercise. But we could also say, explain that further, if we say, what's the formula for cardiac output?
Heart rate
U equals stroke volume.
Stroke volume times heart rate.
Stroke volume. So if we're talking about cardiac output max, then we're talking about heart rate max times stroke volume max. What happens to heart rate max as exercise intensity increases?
Nothing.
Stays the same. What happens to stroke volume max as exercise intensity increases?
Stays the same.
Stays the same. Therefore, cardiac output max stays the same because heart rate max and stroke volume max stay the same. Okay. On your table ends at max cardiac output. You need to add another row on there for submax cardiac output. Okay, so this is during exercise. What happens to submax cardiac output as exercise intensity increases?
Increases?
Increases.
It increases. Trying to see where that background noise is coming from. You guys need to mute your microphones, please. Okay, so let's talk about why cardiac output submax would decrease. Cardiac output submax is going to equal heart rate submax times stroke volume submax. Okay, what happens to heart rate submax as exercise intensity increases?
Increases.
It increases. Why?
Because of the decreased PNS activity and the increased SNS activity.
Good, and you have details for that, right? So you can give a detailed explanation of what's causing the increases in heart rate during exercise. What's happening to stroke volume submax during exercise?
Increasing.
It's increasing. Why?
Increase
The left
in
ventricle.
Go ahead.
increase in venous return, increase in ventricular
Distensibility.
Sensibility, increase in left ventricular contractibility, and a decrease in resistance.
Good, and you should relate those to end diastolic volume and end systolic volume. Okay, so that's a short answer for this, but you also have a much more detailed answer you could put there. So you need to connect those here. Okay, we understand what's causing the increases in heart rate during exercise. We understand what's causing the increase in stroke volume during exercise, and those two things together explain the increase in cardiac output. Okay, this is another good test question. Explain in detail what's causing the increases in submax cardiac output during exercise. In order to do that, you have to explain in detail what's causing the increases in heart rate and what's causing the increases in stroke volume. Make sense? Okay, so I'm gonna stop there. We finished the first side of the table. So on Monday, we will finish the other side of the table and probably start on the next chapter, which will take us into training. Okay, and so we're gonna start to get more and more applied. And so what I'm thinking of in terms of the final is making it more applied so that I don't have to worry so much about if you have your notes in front of you. I'm thinking about maybe even making it open note, but then the questions won't be copying things from your notes, it'll be more applied. So it'll be things that aren't in your notes, but you'll have to know how to apply the information that is in your notes to situations. So we're gonna spend some time as we move forward in these next few chapters. I'm gonna spend more time applying it and less time worrying about memorizing lists. Okay, but you need to make sure you understand this terminology. Okay, if you're not comfortable with the terms stroke volume, cardiac output, end diastolic volume, end systolic volume, lactate threshold, if you're not comfortable with those terms, you are not going to follow anything that's happening in the next couple chapters, because we're going to be using all of those concepts and talking about how they're affected by exercise and training. Okay, so if you're behind on that, make sure you spend these next few days catching up so you can stay with us as we start to apply it. All right, you guys have any questions for me?
Yes, I have a question. Doesn't really have to do with the information here. For the recordings, I tried looking for them on Canvas. Where would you find them?
Cindy is doing the recordings. Are you posting them, Cindy?
Yeah, they're under, so if you go under people, there is a group. They're under that group, and they're also in the chats. They're posted in 2 places in Canvas.
Okay.
So there's like a discussion?
Yeah, it's like an announcement in the discussions, and then there's like a chat in the chat.
She also sends them out like an email, so you get like an email from Canvas saying, "Oh, YouTube link," and then that link will send it to YouTube.
That's how I always get through the link. So yeah, it works.
Okay. And thank you, Cindy, for doing that.
No problem. Yeah, if your school email is attached to it, you should be getting the email for it every time I send it out.
Great. Any other questions? So please spend some time. I won't see you again until Monday. Please spend some time going over this information so that you're comfortable with it so that we can move forward. All right. Otherwise, have a good day. I'll stay on here for another couple minutes in case you want to stay and ask a question. Otherwise, I will see you guys next Monday or in office hours.
Bye.
Thanks, Professor.
Thank you.
You're welcome.
Thank you, Professor.
Everybody's waiting to see if someone else has a question.
I have a quick question.
Yeah, go ahead.
So like I knew my stuff for this exam, I felt like, and I really struggled with like time, and like I felt like the whole time I was just like going super fast and like not being able to check anything and all that. So like, is there any suggestions you have for the next exam on like how to balance my time better, I guess? Cause like, I think I only had like 3 or 4 minutes left and I was like, oh my God, the whole like test.
Were you able to finish?
Yeah.
Okay, but you were really rushed at the end.
Yeah, I felt like I couldn't like what after I put my answer, I couldn't really like, oh, is that right? You know what I mean? Like sort of like recheck.
Yeah, pacing yourself on an exam like that is completely different than what you're used to. And I understand that, and that was true for everybody. I'm thinking about some different ways to solve that, like maybe separating the multiple choice. The multiple choice has its own time block, and then the short answer has its own time block.
Mm-hmm.
So that helps you pace yourself a little bit more. I
Yeah.
might do that. And I'm also open to suggestions on how it would make it easier for you guys to manage that, because I know it's challenging.
Okay.
I want to say thanks for.
I'm sorry?
I appreciated that you put all the short answer questions in the beginning because I felt like, okay, at least now I know that once I'm done with this, I can speed through the multiple choice if I have to.
Yeah, I think that definitely worked better. The first class that took it had the multiple choice first, and it was a mess. So yeah, I'll definitely do that again, or separate them.
I'm the other way around.
I mean, I think we're used to having the multiple choice first. That's how I usually set up my test, but I know some people turn and do the short answer first anyway. But when you can go back and forth, you're in more control and you can pace it. So I think if I put them in their own time blocks, it'll help you with the pacing.
Did we know ahead of time how?
Your microphone went out. Say it again.
Did we know ahead of time how many were multiple choice and how many were short answer? Did I miss that?
Yeah, no, I don't think I told you that in advance.
Oh, okay.
I just gave you a general idea that there would be multiple choice, and some were going to be, you were able to select more, select all that apply, and some were going to be matching, and some were going to be fill in, and some were going to be drop down, and then you'd have a bunch of short answer. And that different people were getting different questions. That'll happen on the final as well.
Professor, there was also, I got like questions that had like blanks on them. And the first one I knew what to do, and I know I got that one wrong because that was my mistake. But the second one, it had me like match, but there was like
there was a
one
match question that had a blank one. Yeah, I'm giving credit for that. I can see that as I'm scrolling through and grading it. I'm making sure to give you credit for that. That was my mistake on how I was building the matching question.
Okay, thank you.
Could you go over just super quickly how heart rate submax increases with the exercise intensity? Because I want to make sure I don't miss anything when I'm explaining it thoroughly.
Think about this. Remember this drawing? This is intensity. Let's spell it correctly. This is heart rate.
Is this the graph for external control of heart rate?
Extrinsic control of heart rate, yeah. So increases from 60 to 100 due to decreased parasympathetic activity and decreased vagal tone. Increases above 100 were due to increased sympathetic nervous system activity through the sympathetic cardiac nerve and epinephrine. So that's the same question. What's causing the increases in heart rate during exercise? Does that make sense?
Yeah, I remember that was like a short answer question on the test. And I think I was just so focused on blood pressure that I totally forgot about the decrease and the increase in the two systems. But thanks for that. That helped.
You're welcome. All right, you guys have a great day. Have a good weekend.
Thank you so much.
Thank you.
You're welcome.
Thank you. Thank you.
Bye.